Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to give an introduction to the idea of binomial expansion. And here we have a problem of basically trying to expand this expression. What's the result of this? And obviously, if n is small, okay, so if n is small, it is not that bad to try and get the result of the expression here. For example, if a plus b is 0 when n is 0, the result is obviously equal to 1 because anything with a power 0 is just 1. When a plus b, when n is 1, this is also quite easy to get the result. The result is just a plus b. When a plus b with n equals to 2, this is something that a lot of us are already familiar with, done it a lot of times. The result is just a squared to ab plus b squared. Now, if you have a plus b where n is equal to 3, it's getting a bit tedious, but still doable, okay? So this is equal to this guy here times with a plus b, and you can do it by multiplying all the terms properly, okay, accordingly. So here a squared with a, you get a cubed, a squared and b, 2aba, 2abb, okay, b squared a plus b squared with b, b cubed. You simplify that so that you can get the final result. It's going to be a to the power of 3, a squared b, a squared b. So that becomes 3 a squared b. So this is done, this is done, this is done. ab squared, b squared a, 3 a b squared, the same thing, done and done. Finally b to the power of 3 or b cubed. So that's the result for a plus b to the power of 3. But then I'm sure you will agree with me that if you have a plus b where n is equal to 4, it's getting really tedious to do this calculation. A plus b to the power of 5, well, it's getting even more tedious. And basically, you know, what happens if n gets really big? How are we going to get the result of it? So when we come to big n, when n is big like 4, 5 and so on, we need a special help, okay? So we need a special tool, and the tool here is in the form of Pascal's triangle. So I think this is really helpful in order to help us expanding the expression given here. For example, what is the result here? You should use Pascal's triangle. This one, what is the result, and so on, okay? So in the next slide, I'm going to talk about this Pascal's triangle. Okay, so here is about understanding the Pascal's triangle, and as the name suggests, it is going to be in the form of a triangle. So how to create this Pascal's triangle? It is quite easy. First of all, it starts with number 1 at the top, and then the next line we will have 1 and 1. The next line we will have 1 and 1. We're going to fill up this with the result of 1 plus 1, which is 2. Okay, move to the next line, 1 and 1. Fill up these spaces here with the sum of 1 plus 2 is 3, 2 plus 1 is 3. So you put the position of it in the middle here. Okay, so now 1 and 1. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. 1 and 1. 1 plus 4, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. Okay, we can go on and on. 1 plus 5, 6, 5 plus 10, 15, 20, 10 and 5, 15, 5 and 1, 6. So basically that is the construction of a Pascal triangle, and you can actually go on and continue on if you like. But let's say we stop right here, okay, just to illustrate the process of getting the Pascal's triangle. Now, how can this Pascal's triangle relate to the problem of finding a plus b to be n? So how can we use this? Well, if you look at this line here, this is you can think of it as the position where you have a plus b 0. The result here we all know is equal to 1. For this one here is a plus b 1. This is a plus b, very easy. Now this is where I think it gets interesting from this point onwards, okay? So for this one here, it can be thought of as corresponding to the problem of finding a plus b squared. And the result here is, as you can see, we have 3 terms, 1, 2, 3. So we have 3 terms to add on. Well, 1 and 1 here will correspond to the fact that we have 1 times a squared, 1 times b squared. And next is 2. 2 is for the coefficient right next to a and b. Okay, let's try again this one. So this is a plus b cube. We have 1, 2, 3, 4 terms. 1, 2, 3, 4. Again, 1 and 1 correspond to the fact that here we have 1 a cube, 1 b cube. Done. Next is 3 and 3. Correspond to the combination of a and b together, but then here we have different possible a and b. So you can see that here, let's look at position a first. We start with a3, so over here is going to be a2, the power gets reduced, a1, you don't have to write 1, and this one is actually, okay, let us write 1 just for the fact of, just to make things more clear. So a3, a2, a1, this is actually a0. Okay. Now what about b? For b, this is actually the position of b0. So here is b1, power gets increased, b2, and here we have b3. So I hope you can see the pattern right here. But of course, you don't have to write b0 because this is just equal to 1. You don't have to write 1 because 1 times a to the power of 3 is just 1, right? This one, b, you don't have this, you don't need that. Also, you don't need this because a to the power of 0 is just 1. So everything looks a bit more neat and tidy, okay? Right, well, I thought or I feel like you have understood that part. Now let us try with more examples, okay? Let's just play around and get ourselves comfortable with all this. This one, okay? A plus b to the power of 4. We have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So 1 and 1, get it out of our way. A to the power of 4, b to the power of 4. 4, 6, 4. So 4, 6, 4. Look, here is a to the power of 4. Therefore, over there is a to the power of 3. It gets reduced. The highest power is 4. The highest power is 4. 4. So therefore, this is a to the power of 3. A to the power of 2, just a to the power of 0. You don't have to write it because a to the power of 0 is 1. over here is actually b to the power of 0, but b to the power of 0 is 1. You don't have to write it again. So here b to the power of 0, keep that in mind. Therefore, here must be b to the power of 1, b squared, b cubed. Here is b to the 4. Okay, that's it. How simple is that? Okay, we have managed to get the result of this expression here without having to do tedious work. Okay, now let's try and do another example till you get yourself really comfortable with this. Now here is a plus b 5 to the power of 5. How many terms we have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Get rid of 1 and 1, so we know that highest power is 5, a to the power of 5, b to the power of 5, and we are done with that. Next, 5, 10, 10, 5. So 5, 10, 10, 5. The next part is, well, here is a to the power of 5. The power gets reduced. That means a to the power of 4, a to the power of 3, a to the power of 2, a1. Here is a0, which is 1. At this position is actually b to the power of 0. Have that in mind, b to the power of 0. Therefore, over here must be b to the power of 1, b2, b3, b4, and here b to the power of 5. That's it. Last example related to this Pascal's triangle given here. Well, this is actually a plus b to the power of 6. 1, 2, 3, 4, 5, 6, 7 terms altogether. 1, 2, 3, 4, 5, 6, 7. 1 and 1 is allocated for this one, a to the power of 6 and b to the power of 6. 6, 15, 20, 15, and 6. Now here we have a to the power of 6 and the power will reduce. A to the power of 5, 4, 3, 2, 1, 0. A to the power of 0, which is just 1. Next, here is b to the power of 0. It is not stated here because we all know b to the power of 0 is just 1. So b to the power of 0, this here must be b to the power of 1, 2, 3, 4, 5, and over here is 6. Okay, and we are done. Now, how easy is that? All right, next. I also would like to mention the fact that for this one here, well, these numbers here also relate to the idea of combination. Choose C out of N, that kind of stuff. Choose X out of N and so on, okay? So I'm just going to explain a bit on that. So here is actually you have N items, choose 0. This one is actually 6, choose 1, 6, choose 2, 6, choose 3, 6, choose 4, 6, choose 5, 6, choose 6. And the same idea is applied to other lines. For example, if you look at this over here, what it means is you have 4 items, so 4 choose 0. This one here is actually 4 choose 1. This is 4 choose 2, 4 choose 3. This one is 4 choose 4. So that's the idea, okay? Now, if I ask you what would be the formula to find this guy here, a plus b to the power of n. So here we have a plus b to the power of n. So according to the patterns that we have observed on this part, I'm sure you will agree with me if I say that for the first position here, it's going to be NC0. Okay, look at the pattern. Look at all the pattern that we have. Look at whatever that you have managed to observe before with all the examples given. Okay, so here must be NC0. A will start with the power of n and b with the power of 0. I hope you agree with that. And then the second term is of course NC1. Okay, where you have a, the power of a here is reduced by one number from 6 to 5, for example, from 5 to 4 and so on. So here we know that power here is going to be reduced by 1, that means n minus 1, and over here is b. If this is 0, it is going to be increased to 1. Okay, so this is what's going on. If you go on, so that means you choose NC2, the third term. So here we will have a, n minus 2, b2. So that's the idea. And you can keep on doing this until you reach the few last terms. So the last terms will be, so the last term here, let's say this is the last term, it will be NCN, right? NCN, where a here is going to be reduced to 0 and b here is going to be at the highest power, which is n. So that is going on for the last term, NCN, A0, Bn. The second last term must be NC. If the last term is n, choose n. This must be choose n minus 1, right? Over here must be A1, because here is A0, so this must be A1, and here is Bn minus 1. So basically that is A plus B to the power of n. That's the formula. And I'm sure that what is going on here is this long formula here can be written in a compact form. Okay, you can make it more concise and precise by using the sigma notation, because this is just all the summation process. Therefore, okay, I'm just going to erase this part. Where, okay, hang on. Okay, what's going on here? Okay, so I just need this little space here to continue my discussion. Hang on. Okay, so from this long process here, we can make it look more tidy if you consider a plus b. So if you consider, well, you can see that what is changing in this expression is just, well, this part. Okay, so 0, 1, 2, blah blah blah, but you have the same construction. Okay, basically you can write down and see x, this one change, keep on changing, so n maintains, and cx, this one is a n minus 1, n minus 2, so that means this is n minus 0 actually, which is equal to n. Yeah, so this is must be n minus x, 0, 1, 2 and so on, so this is bx. And we can consider sigma notation where x is equal 0 until n. So here we have 0, it starts from 0, 1, 2 until n, so we know that that's the value of our x here. N minus x, n minus 0, n minus 1, n minus 2, and so on. And here is 0, 1, 2, and so on, so bx. So that is the long process here can be written in a more precise manner, compact, okay, in a compact form, okay. So that's what's going on here, and I'm sure you recognize that that this is just n x equals to 0, nx, yes, this part here is nx, bx, a n minus x, and this is something that you have seen before. This part here is just the probability distribution for binomial random variable, and therefore according to what we have managed to show, this one here is equal to a plus b n. Okay, right. So let me just conclude this thing altogether. Based on what I have presented to you, we know that if you have this process here, x equals to 0 until n, here we have nx, a n minus x, bx. This is the same thing as having x0 n and x. You can choose to switch the position, bx, a n minus x. It's okay to change the position of a and b, so a n minus x, and this is just equal to a plus b to the power of n, and this is the conclusion that we need in order to perhaps solve other complicated questions. For example, okay, so I'll give you example 1. If let's say you come across this expression, n y equals to 0, n y p e to the t y 1 minus p n minus y. Now you can directly compare to the conclusion that we have in this purple box here, and you should be able to see that this is just something similar to a plus b to the power of n. So here we have x from 0 until n. Over here we have x, and this is n minus x, n minus x. Of course here we have nx, yeah, so we can take a plus b to the power of n. So again, here we have y equals to 0 until n. Over here we have n minus y and y. Therefore you should recognize that this has the same form as this one here. The difference is in b and a, so you can take this as, you can think of it as b and this is a, right? So the answer to this expansion problem is just going to be 1 minus p plus PET to the power of n. Okay, so that's it. Second example. Okay, let's say you have this expression to evaluate. M t equals to 0. M t p t q m minus t. Again, you should recognize it has a similar pattern to what we have in this purple box here. So you can see that here we have t equals to 0 until some value of m. Over here we have m minus t and t, and right here is um, the process of choosing t out of m and so on. Okay, so p to the t q to the power of m minus t. Therefore, the result of this is equal to q plus p to the power of m. Okay, so basically you are using this important result here, and you will do some sort of comparison with the question given, and you can easily come up with the easy expression to the one given here. Okay, I think that's the idea really about the binomial expansion, and I hope that this is beneficial to you, and it will be able to, and you'll be able to use it for, you know, the parts of um, proving MGF and so on. Okay, so that's it really. Thank you very much for watching.